Okay, Chapter 1, Section 4, Rational Expressions. In this section, we will cover the domain of an algebraic expression, simplifying rational expressions, multiplying and dividing rational expressions, adding and subtracting rational expressions, how to deal with compound fractions, rationalizing denominators or numerators, and finally, avoiding some common errors. Okay, so a quotient of two algebraic expressions is called a fractional expression. Here are some examples. Okay, so you can see 2x over x minus 1, y minus 2 over y squared plus 4, x cubed minus x over x squared minus 5x plus 6, or x over the square root of x squared plus 1. What do all these have in common? It's a giant fraction, right? It's a division of two algebraic expressions. Okay, now a rational expression is a fractional expression in which both the numerator and denominator are polynomials. So the first three in these examples fit the definition of a rational expression. It's a polynomial divided by another polynomial. It's a giant fraction where both the numerator and denominator are polynomials. That's what we're going to be focusing on in this section. This last one is a fractional expression, but it doesn't quite fit the definition of a rational expression because of the giant root here, the square root of x squared plus 1. So that's something else entirely. That's not a rational expression. Nothing wrong with that. It's a great mathematical statement, but it's just not the focus of this section. Okay, so we're going to be focusing on rational expressions. Rational, fractional, fancy word for fraction. So it's a giant fraction with the numerator and denominator both polynomials. Okay, first of all, the domain. The domain of an algebraic expression. So in general, an algebraic expression may not be defined for all values. And there are two main concerns when we're dealing with these. When you're asked to find the domain, you got to ask yourself one of two main rules that we have to think about. So far, we know that we are not allowed to divide by 0. So we can't have a fraction. So we know so far that we can't have a fraction where we have something, say a 1, divided by a 0, right? We don't want to deal with that. We don't want to divide by 0. And we don't want to deal with anything where we have a square root of a negative number, because we know that that leads to an imaginary number, right? The square root of -3, the square root of -4. That's an imaginary answer, and we don't want to deal with those. We want to stay within the domain of real numbers. Going along with that, it's not just the square root, it's any even root, right? So if we have the fourth root of a negative, we're also going to end up with imaginary numbers. We don't want that. So if we had a cube root of a negative, then that's okay. That's not going to lead to an imaginary number. Good? Okay, so most of the time we really just deal with these two. Cases where we're dividing by 0 and cases when we're taking the even root or the square root of a negative. So here's a little summary, right? So the domain of an algebraic expression is the set of all real numbers that the variable is permitted to have without violating one of these rules, right? So we like to, by default, stick to the real numbers, so we don't want to go into negatives. We don't want to go into the imaginary domain. So 1 divided by x, what is the domain of this? When they ask you for the domain, really we kind of flip it around and think about the things it's not allowed to be. And it's not allowed to be 0, right? Because then we'd be dividing by 0. So the domain of this is all real numbers except the 0. This notation here, because the only thing we've identified is that x cannot be 0, this is the same thing as saying all real numbers except 0. All real numbers except 0. Right? That's what this is saying. Okay, in here we have the even root of x, the square root of x, and as we noted, we don't want any negatives. So this is saying we are allowing x to be all numbers that are greater than or equal to 0. All real numbers that are greater than or equal to 0. All real numbers greater than or equal to 0. Right? So it's x such that x is greater than or equal to 0. And then finally, the last one, we have two things to consider. First of all, if we just think about the even root here, the square root of x, well, that's this. We can't let x be equal to a negative number, so we would allow x to be 0 or greater, equal to 0 or greater. But then when we think about the fact that it's also a fraction and root x is in the denominator, we also incorporate this part where x is not allowed to be 0, because then we'd have a 0 in the denominator. And so if we combine those two things, we end up with this as our domain. The domain is all real numbers that are strictly greater than 0. Okay, so finding the domain means you make a list of all the values you're allowed to plug in. Sometimes, in very rare cases, that list of things you're allowed to plug in is very, very limited. Like, let's say, for example, I wrote a computer program and the variable grade, right, when I submit the grades at the end of the semester, the variable grade can only take on a very limited number of values. Let's say grade was just the letter G. So then if I wanted to find the domain of G, right, it's the grade, letter grade, domain, then the domain would be very, very limited. It would be the letter A, it would be the letter B, the letter C, the letter D, and the letter F. Those are the only grades I'm allowed to submit. So writing down the domain is pretty easy to write it down this way, because there's not that many options. Okay, so sometimes you have a very restricted, very simple domain you can just simply write down. But when it comes to the cases we deal with, the domain is going to be almost always a infinitely large set of numbers. So it's impractical, maybe almost impossible to write them all down in many, many, many cases. So very often, rather than writing down the numbers, it's just easier to identify the ones that we cannot have. So that's what this is here in this first case. Instead of writing down all the things you can put in there, x can be a 2, x can be a -7, x can be 3.5, x is allowed to be pi, right? We can write down all the things it can be, but it's just a lot easier to simply point out what it can't be and then assume everything else is fine. So that's a very, very common thing when we're finding domains. Flip the question around. Think about what can't it be? What is it not allowed to be? And that'll lead you to figure out the things that it is allowed to be. Okay, let's look at some examples. The first one, okay, what kinds of values can I allow x to be and not violate one of my two rules? Remember, there's only two rules. You're not allowed to divide by 0. You're not allowed to take the square root of a negative number, the even root of a negative number. And well, that's not going to happen here no matter what I do, right? If I let x equal to 2, okay, x equals to 2, x equals to 2, I'm not going to violate one of those two rules. If I allow x equal to a fraction, how about 3 over 2? 3 over 2. Still, no problems, right? I'm not dividing by 0. So there isn't anything I can input for x. There is no real number that would give me a problem. Even if I put in 0, right? X could be 0, x could be 0. No problems there. So the domain is all real numbers. All real numbers. All real numbers. You can write it all out. You can also describe it this way, from negative infinity to positive infinity. It's the set from negative infinity to positive infinity. You can also use this notation of capital R. It's all real numbers. Any way you describe it, the domain is anything, all real numbers. Okay, moving on to number 2 then. Okay, so in this case, now we do have to be careful because there could potentially be a value of x such that if I put in a value, that particular number, it could be that the denominator equals 0, and then I would be dividing by 0. So that's something we have to avoid. So in order to solve it, we pull that off to the side. So let's pull out the denominator off to the side. and use our awesome algebra skills to figure out what that is. If I can find the x values that make this true, if I can find the inputs for x that would result in a 0 for this denominator, I would find the values that result in a fraction with a 0 in the denominator, and then I know that that violates one of my two rules. The domain would then be everything except the ones I find. Okay, so now to solve this, we know we need to factor it. This fits our fourth factoring technique, right? As we factor this, they don't have any common factors. That's not number one. I can't factor by grouping. Nope. It's not one of my common shortcuts because this isn't something squared. So it has to be the last one. I know that it's going to be something that fits this form. Blank times blank must be 6, and then blank plus blank equals to -5. Keeping in mind that it might be, these guys might be negatives. So a little bit of guessing and checking, right? We can try 1 and 6. They multiply to 6, but they add up to 7. So I know that's not the case. I could do 2 and 3, but I know they multiply to 6, but they add up to 5, not -5. So let's try -2 and -3. They multiply to +6, and they add up to -5. So there we go. That's the answer. And then if I just simplify that a little bit, I can write it as x minus 2, x minus 3 equals 0. And now by the zero product property, I know that if I have two different factors multiplying and equaling 0, I know that at least one of them must be equal to 0. That's what allows me to separate this into two pieces. X minus 2 is 0, or the other case is that x minus 3 equals to 0. If I solve this by adding a 2 to both sides, plus 2, plus 2, plus 3, plus 3, I get that either x equals to 2 is one solution or x equals to 3 is the other solution. And so what I found is the bad things, the things that will result in a 0, right? So let's put over here, check. Let's check it. Check. Note that if I let x equal to 2, then I'll end up with 2 divided by, okay, actually, let me, x equals to 2, I have something squared minus 5 times something plus 6, and there's something there. Let's put it in red. So if we let x equal to +2, I put a 2 there, I put a 2 there, I put a 2 there, and note what happens. We end up with a 2 divided by 4 minus 10 plus 6, which equals to 2 divided by 0, and we have a problem, right? This is not allowed. Undefined. Undefined. Not allowed. So we know we cannot let x equal to 2. Don't let x equal 2. Right? That's the lesson we learned. The other one, let's confirm that the other one is also a problem. If I come back over here and replace each one of those values of x with a 3, get blank squared minus 5 times blank plus 6. And so now if we let x equal to 3, we get a 3 there, we put a 3 there, we put a 3 there, and then we'll end up with 3 divided by 9 minus 15 plus 6. That also leads to 3 over 0. Again, we're in undefined territory. Undefined, right? So not allowed. Don't let x equal to 3. Don't let x equal 3. Okay, so those are the only two situations that result in a problem, something that divides by 0. So then we can conclude then that the domain of this is all real numbers except those two. So domain is equal to all real numbers except x cannot be equal to 3 and x cannot be equal to 2. Okay, that's one way to state it. Another way to state it is with this notation style. Domain equals x such that x does not equal to 3 and x does not equal to 2. Right? By default, this is assumed to mean that x is all real numbers except these two. And then another way you can describe this is by stating or using interval notation. It's all numbers starting at negative infinity, going up to 2, parentheses, right? So not including 2, unioned with 2 going up to 3, open parentheses, unioned with 3 up to positive infinity. That's another way of expressing it. And finally, you can also do it sort of graphically, where you could say that the domain, here's the real number line. Here is -1, here is 0, here is 1, 2, 3. So the domain is going to have a little hole here at 2 and a little hole here at 3, at 2 and at 3. And then everything else is fine. It's all real numbers going out to negative infinity. We skip the 2, and then we connect those two. Any number between 2 and 3, not including of 2 and 3. And then all real numbers going out to positive infinity. We can graph it this way as well. Right? So any way we slice it, that's the domain of this rational expression. Okay, so moving on to the last one here. We have two situations to think about. Number one, we're not allowed to let x equal to a negative value, right? So from here, we want to say that x must be greater than or equal to 0, right? It must stay positive. And then from here, that one's easy. We're not allowed to let the denominator equal to 0. So from here, I can tell that x is not allowed to be 5. X not allowed to be equal to 5, because if we let x equal to 5, we're going to have exactly that same problem. So we just kind of reason our way through it and end up with the following domain. The domain in this case is going to be equal to all real numbers, all real numbers greater than or equal to 0. All real numbers greater than or equal to 0, except, you have to also skip, except x can't be equal to 5. Okay. We can also say that domain is x such that x is greater than or equal to 0, and also x does not equal 5. That's another way of saying the same thing. Or with interval notation, we can also say that we start off at 0. We're allowed to let 0 be a value, all the way up to 5. Don't let it be 5. Union with, starting at 5, go all the way out to positive infinity. That's another way of describing that. And finally, we can also use a graph, right? So here is -1, here is 0, here's 1, 2, 3, 4, 5, 6, all the way out to infinity. And so we want a dark circle around, a closed circle around 0. We want a nice big open circle around 5. It's not allowed to be 5. So it's every value greater than or equal to 0 up until 5, skip the 5, and then every value going that way. And then another way of describing the exact same thing is sometimes instead of a closed circle, we like to stick to the brackets and parentheses notation. So we can also say that it is bracket there at 0, all the way up to 5, and then another parenthesis there, all the way out to infinity. So It's a little more cumbersome in this fashion, but this is another common style. And so here would be the 5 and 0. Okay, I think maybe this one's probably the most popular way of describing this, but in some cases one is easier than another. It's good to just know them all. All right, let's see what your author did. For the first one, it was all real numbers, so we just used that special R symbol. For B, use that set builder notation, x such that x doesn't equal 2, and also x does not equal to 3. By default, that must mean that x could be any other real number except these two. And then for this last one, we wrote it again in set builder notation. It's x such that x is greater than or equal to 0, but x does not equal to 5. Okay, so when you're asked to find the domain, your first instinct should be, is there a value that I can input that will result in me dividing by 0? That should be your first instinct. And next, is there a value that would result in me taking the even root, usually a squared, of a negative number? We don't want to do that. That's going to result in an imaginary number. So those are the two concerns we have to deal with. All right, moving on. Simplifying rational expressions. Super easy. All right, so to simplify a rational expression, we factor the numerator, the denominator, and use properties that allow us to reduce or cancel a common factor. So in this little example, we see we have a product of AC divided by a product of BC, right? Multiplication. The C over C obviously can be reduced. C over C equals to 1. So therefore, this just equals to A over B. Right? That's what this is saying. In other words, you can cancel common factors. We can use that principle to reduce this one. So what we cannot do is simply cancel out this term and that term, right? We can't do that because this is a subtraction, this is an addition. It's true when we have a multiplication that we can reduce them because they're another version of 1, but we can't do it when there's addition or subtraction. This is not true. If you get confused by these ideas, think about this. If I have 3 times 2 divided by 5 times 2, okay, well that one would be 6 over 10. In this case, I can reduce the 2's, and I would still end up getting a 3 over a 5. It seems to make sense. Okay, but let's think about this situation. How about if we had 12 plus 2 over 6 plus 2, and someone says, oh, I know, let's just cancel these guys. So therefore, we end up with 12 over 6, right? Because we just canceled them out, so we're just left with 12 over 6. Well, this would just be equal to 2. 6 goes into 12 2 times. But then if we just go ahead and add these, that would be 14 over 8. How is it possible that 14 divided by 8 equals to 2? 8 does not go into 14 2 times, right? 16 goes into 8 goes into 16 2 times. 8 does not go into 14 2 times. So clearly this is wrong, right? This is definitely not the way you do it. We cannot cancel when there's an addition or subtraction, only when there's a multiplication of terms. So don't make this very common mistake of canceling those guys out. Okay, enough of that. So what would you do? What we have to do is factor the numerator, factor the denominator, using all our skills from the previous section, and then maybe reduce, cancel. So using our skills from the last section, we see that this is a difference of squares. So this numerator can be factored into x plus 1 and x minus 1. Right? This is a difference of squares, something squared minus something squared. This all comes from, erase this. This all comes from one of our established patterns, a plus b times a minus b equals to a squared minus ab plus b, a minus b squared. And then the middle terms cancel out, and we're left with just a squared minus b squared. So this is what happens when we FOIL it, and now we know that if we want to go backwards, we see this pattern emerge. If we see something squared minus something squared, it can be factored this way. And that's what we have here. Something squared, which is the x squared, minus the 1 squared. So that's why it factors this way. What about this one? This one factors using our fourth technique. Right, as we go through the various techniques, number one, they don't have anything in common. I can't factor out a common term, a common factor. Not factored by grouping. I need at least 4 terms. It doesn't fit one of my patterns, the denominator. So we got to go with the fourth one, which must mean that if this factors nicely, it must fit this form. X plus blank plus blank, and then x plus blank. You've got to find 2 numbers that multiply to -2 but add to 1. So a little bit of guessing and checking should get us to, let's see, it could be 3 and a minus, could be a 2 and a -1, for example. Those multiply to -2, but they add to +1. So that's the one that fits. Okay, so now that you've factored it, let's come back and regroup this. X squared minus 1 divided by x squared plus x minus 2 is equal to x plus 1 times x minus 1 divided by x plus 2 times x minus 1. And now that everything's being multiplied, I can now reduce these guys. And so my final answer is just going to be the x plus 1 divided by the x plus 2. Nothing else will reduce. That'll be our answer. Okay, so factor the numerator, factor the denominator, cancel, reduce. That's it. This is what your author did, same thing. Factor the numerator, factor the denominator, reduced, and there's our answer. Okay, multiplying and dividing rational expressions. Very, very similar. So here what we have is one fraction times another fraction. And remember, we do not need common denominators when we're multiplying fractions, only when we're adding or subtracting them. So in this case, we just multiply the numerators, multiply the denominators, and that's how we get to our result. Except we also want to take advantage of anything that will reduce before we actually multiply. So here's an example. We could just multiply this, right, and get the correct answer, though it would be kind of a nightmare. I could just say, well, okay, it's this one times this one across the numerators, and then across the denominators, it would be this one times that one. Okay, and then I can just start my foiling process and get an ugly 6-term polynomial divided by another ugly 6-term polynomial, and that would technically be the correct answer, but it wouldn't be very pretty. So instead of doing that, what we're going to do is take each one of these terms piece by piece and factor it. Each one is really not that bad. X squared plus 2x minus 3, that's going to be x plus blank times x plus blank. 2 numbers that multiply to -3 but add to +2. That's going to be a +3 and a -1. They multiply to -3 but add to +2. Good. Okay, so that takes care of that term. This term, we're going to factor out the 3, so we'll just end up with 3 and then x plus 4. Nothing to do there. And then this one fits one of our patterns. It's true that the first term is something squared, the last term is something squared, and the middle term happens to be twice the 2 things that you're squaring. So it fits our pattern that it's going to be this plus this squared. So this last one factors as x plus 4 squared. All right, let's redo the whole thing. We end up with x squared plus 2x minus 3 divided by x squared plus 8x plus 16 times 3x plus 12 all over x minus 1. And that's going to be equal to x plus 3 times x minus 1 divided by x plus 4, and I'm going to separate it because I'm anticipating something will reduce. X plus 4 times x plus 4, that's this x plus 4 squared, times, and then I had a 3 times x plus 4 divided by an x minus 1, and that's from here. So this factored into that. This one factored into the product of those two. This one factored into that one. And then the last one, well, it didn't need to be factored. Right? So we were able to break down each one of these trinomials into these two, and this binomial factored into that. And now that we have it like this, we can go ahead and reduce. So let me get rid of all these things. Kind of messy. So now we can actually reduce. So this will cancel with that one, and one of these will cancel with that one. And so what we have left over is this term times that term. So it'll be 3 times x plus 3 divided by, in the denominator, we only have that one left over, x plus 4. That's a perfectly good way to stop if you want to say that that's my final answer. Or I think most people would expect you to distribute it there and get a 3x plus 9 divided by an x plus 4. I think either one of those would make a fine final solution. Okay, hopefully that's clear. Not difficult to multiply rational expressions. It's just that it requires a lot of factoring. Right? So really this is just a section that really tests your ability to factor polynomials. Okay, so same answer. All right, dividing them. If we had to divide one fraction divided by another fraction, remember that we can use this pattern. It's to leave the first fraction alone, change the division to a multiplication, and then flip, find the reciprocal of the second fraction, right? So that's a common way people remember it. Keep, change, flip, right? Or the numerator or the first term multiplied by the reciprocal of the second term. Any way you've memorized it is fine. So we just need to apply that, and then that turns itself into a multiplication of fractions, which is what we just did, right? That coupled with all that factoring will help us solve these guys, no problem. Okay, so step number 1 is to get rid of that division symbol right there. So what we're going to do is keep the same first fraction. So that'll be x minus 4 divided by x squared minus 4. And then we're going to multiply, so instead of division, times, and then the reciprocal of the second fraction. So that'll be x squared plus 5x plus 6 divided by x squared minus 3x minus 4. Okay, so we got rid of the hard part here, getting rid of that division symbol. And next, we just have to factor everything. So how do we factor this guy? Well, that's going to be a difference of squares, right? That's something squared minus something squared. X squared minus 2 squared. Something squared minus something squared. So from our patterns, we know that that must mean x plus 2, x minus 2. Okay, how do we factor this guy? We need x plus blank times x plus blank. And I need to fill out the blanks. I need two numbers that multiply to -4, but add to -3. So -4 and +1 multiply to -4 and add to -3. So that works out. Remember that I knew it had to be this pattern because there's a nice pretty 1 out in front. If this original polynomial had something more complicated like a 2, then I would have to do it by the AC method, which is a little more complicated, right? Or the guess and check method. Okay. This guy, again, an easy trinomial. There's a nice pretty 1 out in front. So I know that it's got to be of this form if it has a nice solution. So I need two numbers that multiply to +6, but at the same time add to 5. So you can think about 1 and 6, for example. They multiply to 6, but they add to 7, so they can't be it. But if we do 2 and 3, they multiply to 6, but add to 5. There, so that takes care of it. So let's copy that whole thing down. This product now, this multiplication, is then going to be equal to x minus 4 divided by x plus 2 times x minus 2 times x plus 2 times x plus 3 divided by x minus 4 times x plus 1. Good. Okay, so now we get to do some canceling. This and this one reduce, and the plus 2 and the plus 2 reduce, and that's it. Nothing else reduces. So the only thing that survives in the numerator is going to be this one, and in the denominator, the only thing that survives, so we have x plus 3 in the numerator. In the denominator, we end up with an x minus 2, and then x plus 1. It doesn't reduce any further, so that could be one great solution. We could stop there. Or in some cases, you might see some people pushing for you to go ahead and expand this, FOIL it all out. And so you might see either that solution, or if we FOIL this out, we end up with x squared. This times this is x squared. This times this is x. Minus 2x is just going to be minus x minus 2. Right, so that's the other great possible solutions, right? As you're checking in the back of the book to see if you have the right answer, you might see this back there, or you might see this. I'm happy with either one. And just to make sure it's clear, we're talking about this original one. So we're saying that the original x minus 4 over x squared minus 4 divided by, and then we had x squared minus 3x minus 4, and then x squared plus 5x plus 6, that this is equal to this one or that one, right? Either one of them. The division of these two rational expressions, rational polynomials, rational fractions, is equal to either this one or that one, either one. Okay, so not too difficult, right? We just have to, again, really heavily rely on our factoring of polynomial skills to be able to break each one of these down and reduce them. Hopefully they're not too bad. Let's see what the author did. Same thing. So we change the division over to multiplication, keep the first fraction, flip the second fraction, factor everything, and then cancel common factors, and looks like the author stopped there rather than FOILing it all out. Either way is fine. Okay, adding and subtracting rational expressions. Okay, so we know that when we're adding two fractions, we need a common denominator. So if the original question already has a common denominator c, then it's super easy. All we have to do is add the numerators, keep the same common denominator, and then we're done, except once again we might try and reduce the final answer. On the other hand, if the original question doesn't have a common denominator, then you're going to have to fudge it a little bit, find a common denominator, the least common denominator, and then you're going to have to go back to each fraction, manipulate it so that both fractions have the same denominator, and then you can go ahead and add them and subtract them. Okay, so for example, let's say we're asked to add this one. If it was an easier one, let's say we just had 3 over x plus 2 plus x over x plus 2. See, in this case, both fractions have the same denominator. This one's an easier one. This one's just going to be 3 plus x divided by x plus 2. Right? We keep the same denominator. We keep the same denominator and add the 3 and add plus the x plus the x. And we keep this same denominator. The same denominator is just, we keep it. So that's the case where we have a simpler situation. But here we have a more complicated case where they don't have the same denominator. So the first thing we have to do is think about how to get both fractions to have the same denominator. We need to find the least common denominator, least common multiple between the two. And so the simplest way to figure that out is just to multiply them together and use that as the common denominator. So common denominator is going to be equal to the multiplication of the two. The easiest way to get there. Okay, so let's copy this down. We're going to have 3 over x minus 1 plus x over x plus 2. What I'm going to do is I'm going to multiply this one by a 1, multiply this one by a 1. I'm allowed to do that. Anytime you multiply 1 times anything, you get that same value. We haven't changed anything. So let me copy this down over here. Minus 1 plus x over x plus 2. Now here, the version of 1 I'm going to choose is going to be the case of x plus 2 over x plus 2. That's a new version of 1, right? And then that results in a product in the denominator here that's equal to 1 copy of each, x plus 2 times x minus 1. That's going to be that common denominator. In the other case, I'm going to choose a new version of 1, which is the case of x minus 1 divided by x minus 1. That's another version of 1. So I haven't changed the fraction again. So again, I can simplify this to be 3 times x plus 2 all over x plus 2 times x minus 1 plus x times x minus 1 all over x plus 2 times x minus 1. And now that they both have the exact same denominator, I can rewrite this to be equal to 3 times x plus 2 plus x times x minus 1 all over a common denominator of x plus 2 times x minus 1. Good. Now we just distribute, 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 and distribute. Combine like terms, simplify. If something can be factored and reduced, we would go ahead and do it, but that's probably not going to happen here. So we'll end up with 3x plus 6 plus x squared minus x all over x plus 2 times x minus 1, which then, okay, we have a common denominator here. This term and this term are like terms. They add up to 2x. So this will be equal to x squared plus 2x plus 6 all over x plus 2 times x minus 1. Now, if the numerator factored into something nice, we would go ahead and factor it. Two numbers that multiply to 6 but add up to 2. We have 2 and 3. That's not going to work. 1 and 6. That's not going to work. So there aren't any nice ways for this thing to factor with the nice whole numbers. So this would be a good place to stop, or if we wanted to break this down, it seems a little weird that this one's factored out and this one isn't, so we might want to go ahead and factor it out. Plus 2x, FOIL out the denominator. And if we FOIL out the denominator, we'll get x squared plus x, minus x plus 2x gives me a plus x minus 2, and that would be a good place to end. So bringing the original question down, we end up with 3 over x minus 1 plus x over x plus 2 is equal to this. Looks like the author wasn't afraid to leave it alone like that. Okay, that's fine. We can leave it in this format like this, or like I said, I just think it's a little weird that the denominator is factored and the numerator is not. But that's my own personal struggle. Either way is fine. I would accept either one. Okay, moving on. What about something like this? Again, we want to find the least common denominator. So the first thing I would do is factor out everything. So this guy, we have something squared minus something squared. This factors as x plus 1 times x minus 1. And well, this one is just x squared plus 1. X plus 1 squared, sorry. So it's just two copies of this thing. Okay, so the least common multiple, the LCD, the least common denominator, least common divisor for these, the least common denominator in this case, is going to be to use the x plus 1 and the x minus 1, right? Because this has x minus 1, this has x plus 1, so we got to use both of those. And then notice that we got to use 2 of these. So x plus 1 squared times x minus 1. Right? We can always introduce a new factor, so we can easily multiply an extra term of x plus 1 here in order to get to this LCD. And we can always introduce a next term of x minus 1 to this one in order to get to this LCD. So if, for example, let's go over here on the side, if we wanted to find the least common, the LCD between, say, 40, say we had x over 40, and we want to add it to, I don't know, b over 60, and we wanted to find what is the least common multiple between 40 and 60. Okay, one way to do it is to find the prime factorization of each of these. So that'd be 4 times 10, 4 times 10, which then gives you a 2, 2, and a 2 and a 5. So that'd be 2 to the third power times 5. And this one is 6 times 10, which is a 2, a 3, and then a 2 and a 5. So this is 2 to the second times 3 to the first times 5 to the first. Okay, so the LCD is going to be to write down the base numbers you see once. So there's a 2, there's a 3, and there's a 5, right? There's a 2, a 3, and a 5 somewhere. And now you go back and you write down the biggest exponent that appears for any one of these. So for the 2, we have a 3 there, and we have a 2 there, so we use a 3. And then for the 3, well, it only appeared once, and it had a 1, so we had to put a 1 there. And then for the 5, it only appeared once, and it had a 1, so we put a 1 there. So this is 8 times 3 times 5. 8 times 3 times 5. 8 times 3 times 5, that's going to be 24 times 5, which is equal to 120. 120 is the least common multiple, right? So in other words, when I come back over here, I can multiply this by 3 over 3. That gets me to 120. And I can multiply this by 2 over 2, and that'll give me to 120. Okay, we want to follow that same pattern over here. This guy, if I wanted to break it down, is equal to x plus 1 times x plus 1. But following this pattern, I know that I have an x plus 1 and an x minus 1 somewhere. And then the x plus 1 has an exponent of 2. That's why I use a 2 there. And the x minus 1 has an exponent of 1, which is why I use a 1 there. Okay, so now that I know that that's my least common denominator, let's come back and fix this. So I have 1 over x squared minus 1 minus 2 over x plus 1 squared. Okay, well then this is equal to 1 over x plus 1 times x minus 1 minus 2 over x plus 1 squared. So for the first fraction, it's missing an extra factor of x plus 1, so we're going to multiply the numerator and denominator by an x plus 1. That's a new version of 1, so that should take care of this. And then this one, we're going to multiply the numerator and denominator by a term of x minus 1 over x minus 1. This will result in two fractions that have the same denominators, right? We achieve this, the LCD. Okay, so this then turns into x plus 1 in the numerator. A denominator has an x plus 1 squared times an x minus 1 minus, and then here we end up with 2 x minus 1 over x plus 1 squared times x minus 1. So both fractions have the exact same denominator, and so then will be equal to x plus 1 minus 2 x minus 1 all over the same denominator, which is the x plus 1 squared times the x minus 1. Okay, so now we distribute this, keeping in mind that this subtraction applies to both terms. So we have to distribute that and distribute that. And so we end up with x plus 1 minus 2x plus 2 divided by x plus 1 squared, x minus 1. Combining like terms, we see that this guy, this one and this one are like terms. So positive x minus 2x gives you the minus x. And then the 1 and the 2 combine. So we end up with minus x plus 3 all over x plus 1 squared, x minus 1. And then usually, well, sometimes we like to leave the minus out in front because it's the variable like this. But very often we like to avoid starting with a negative if we can, if it's a simple fix. So some people might see the answer this way, and some people might flip it around and write it as 3 minus x. Either one is just fine. X plus 1 squared, and then x minus 1. Right? Either one is fine. So I'll say either this one or this one is perfectly okay. And just to bring it together, the original statement was this one. So we're saying that 1 over x squared minus 1 minus 2 over x plus 1 squared. I think that was the original question. Yeah, 2 over x plus 1 squared. That this is either equal to this guy or it's equal to that. Hopefully that was clear. Let's see what the author did. They leave it as a... Yeah, see, the author flipped it around as well. And so here we go. Okay, so hopefully these aren't too bad. Compound fractions. These aren't bad at all, but people don't like compound fractions, so let's spend a few minutes on them. A compound fraction is a fraction in which the numerator or denominator or both are fractions themselves or have fractions in their own expressions. Okay, so here is an example. We have one giant fraction. Oops. Now we have this giant fraction here. This is a fraction where we happen to have another expression with a fraction or a fraction in the numerator, and same thing in the denominator. So how do we deal with these? There's two general ways in which we're going to deal with them. The first way is to treat them separately. Think about the numerator separately from the denominator, figure out a way to combine them and reduce them and turn them into one single fraction. And same thing with the denominator. Find a way to make the denominator a single fraction. So work with them kind of separately. So focusing just on the numerator, one thing I could do is I can rewrite this numerator, a little 1 underneath there, so that I have fractions. I can always take any constant and put a little 1 underneath it and turn it into a fraction. So in the numerator, I end up with x over y plus 1 over 1. Separately, in the denominator, I'm going to do the same thing. I end up with 1 over 1 minus y over x. So I'm kind of just thinking of them separately. How do I combine these into one single fraction? I need a common denominator. Well, that's going to be the y, right? So I'm going to multiply this fraction by y over y, and that'll give me two fractions that have the same denominator. X over y plus y over y, just kind of thinking about the numerator. So that combines into x plus y over y, just focusing on the numerator. So I've accomplished my goal of rewriting the numerator as a single fraction. Now in the denominator, I'm going to do the same thing. Common denominator in this case is going to be an x over an x. So combining them is going to give me the following. I'll end up with an x over an x plus, minus a y over an x. Common denominator is x, so that will result in x minus y divided by x. So again, I've accomplished my goal of rewriting the numerator into a fraction, rewriting the denominator into a fraction, and now we use our common pattern that we've established before, that this is going to be equal to the numerator times the reciprocal of the denominator. So this will result in x over y divided by y times the reciprocal of the denominator, which would be x over x minus y. Right? Finally, we multiply the numerators, multiply the denominators, so we end up with x times x plus y divided by y times x minus y, and then we distribute, before we arrive at our final answer, which is going to be x squared plus xy divided by xy minus y squared. Right? And that's our final answer. Ugly. Of course, if something were to cancel, reduce, we would take advantage of it, but nothing will. Right? Even if we try and factor it, well, then we're just going to get to this stage, and then nothing reduced, so I know it's not going to reduce. Okay, so that's option number one. Treat them separately. Figure out a way to turn the numerator into a fraction, turn the denominator into a fraction, so treat them like two separate little problems until you get to this stage where we have one fraction divided by another fraction, and then we use our keep, change, flip pattern. Numerator times the reciprocal of the denominator, and that way we can rewrite it as a multiplication instead of this ugly division. And when we do that, then we know that when we're multiplying fractions, we don't need a common denominator anymore. We just multiply the numerators across, multiply the denominators across, reduce if we can, otherwise that would be our answer. Okay, so that's the first option on how to do this. I think that that's the same. We'll see what the author does in a second. The other option, the other way to do this, let me copy this over here. So I'll put option number 2. Right, this was option 1. Option 1 is this. Option 2 is going to do the following. We have x, y plus 1 divided by 1 minus y x. We have one giant fraction, but then there's going to be presumably little fractions in the numerator and denominator. So let's focus on all of the denominators of those little fractions. In this case, it's just going to be the y and the x. What we want to do is find the least common denominator, the LCD for all of those, and well, in this case, well, it's just going to be x, y. Right? You just multiply them together. If it was more complicated, we deal with that. And if there was more fractions, we deal with that. We want the LCD of all the denominators of all these little fractions. When we find it, we're going to do the following thing. This, I'm just going to copy it here to make some space here. This is x over y plus 1 all over 1 minus y over x. What we're going to do is we're going to multiply the numerator and denominator by another version of 1. We've seen this trick before, right? Whenever you multiply 1 times anything, you haven't really changed the problem. So this is equal to, again, I'm going to copy it, x over y plus 1 all over 1 minus y over x. But then instead of this giant 1, I'm multiplying the giant fraction, not the little fractions. Multiplying the giant fraction, I'm going to multiply it by another version of 1, which is this LCD that I found. So it's going to be xy over xy. And I'm multiplying the giant, the large fraction over that. So that means that in the numerator, I'm going to multiply this times each of these. And in the denominator, I'm going to multiply this times each of those. Okay? So then I go ahead and do that. This will be equal to xy times xy plus 1 all over xy, 1 minus y over x. And then I distribute, so it's going to be this guy that gets distributed across each one of these terms. So it'll be xy times this fraction, xy times that 1, and then xy times this 1, and then xy times that fraction. So when I do that, I end up with xy times xy plus xy times 1 divided by xy times 1 minus xy times y over x. Okay, so this went there, and this, right? So just distributing across. 1 times anything is that same result, so that doesn't change anything. But what's important is that these little fractions will reduce. The y cancels with that y, and then this x cancels with that x. And so what we get is the following. These ugly things will reduce to just being x times x. Right? It's just going to be this x times that x because the y's canceled. So I'll be left with just x squared plus xy, because 1 times xy is just xy, divided by, and then xy times 1 is also just going to be xy, minus, and then again, these guys canceled, so I'll be left with just y times y. Over here, we have y and we have y. Those two multiply to give me y squared. Y squared. And there's our answer. And it's the same answer we got before, hopefully. So x plus y minus y, x, y, okay. So same answer as before. So we have two options. We can either, option number 1, treat them as 2 separate questions. Figure out what's happening in the numerator, figure out what's happening in the denominator, find a way to manipulate the numerator to get to a point where we have one single fraction, manipulate the denominator separately so that you get to a point where we have one single fraction, and then multiply the numerator times the reciprocal of the denominator, cancel, reduce, distribute, do your magic then. Of course, at any one of these stages, you might have to factor something, and then that gets us to the answer. And then the other sort of slicker, slightly confusing way is to do this, right? Kind of cancel out all the fractions in one big swoop is what we're doing. We're going to figure out the perfect thing to multiply both the numerator and denominator by, such that all those little fractions go away, right? We cancel, reduce all those little fractions, and we end up with something that breaks down nice and easy, and we get to the same answer as before. So 2 options. You don't have to do it both ways, but it'd be nice to kind of understand them both. They have their advantages and disadvantages. Let's see what the author did. So here's the method of working with them separately. Finding a common denominator. Here we made sure that we multiplied this fraction by a y over y. That results in this. Multiply this 1 by an x over x. That results in this. Multiply the numerator times the reciprocal of the denominator. Right? So this is option 1 that we did above. And that gives us this answer. We can also distribute and get a result there. Or then the other way was to work with that LCD. Right? Again, focusing on the denominators of all these little fractions. We get an x, we get a y. That's how we get this xy. That's how we know to multiply the numerator of the giant fraction by an xy, the numerator of the denominator by an xy. And that's the perfect quantity that will cancel out all these little fractions and result in something that's easy to handle. Okay, so hopefully that's not too bad. Next, rationalizing the denominator or the numerator. What does that mean, rationalizing it? Remember, mathematicians don't like roots in the denominator. Square roots, particularly, we deal with a lot in the denominator of a fraction. From time to time, we might be called upon to get rid of the root in the numerator, though that's not as common. So we have a couple of techniques for doing that. For one of the common ways that we're going to deal with this is when we run into a denominator that has something of the form of a plus b root c, and we can rationalize the denominator by multiplying the numerator by its conjugate radical of a minus b root c. Remember, this all roots back, this all connects back, this all connects back to that the difference of squares. We know that if we have a plus b times a minus b, and we FOIL it all out, we're going to end up with a squared minus ab plus ab minus b squared. And then these guys cancel out, the middle terms cancel out. So we end up with a squared minus b squared. So we're going to be going back to this, because if we have a plus b root c times a minus b root c, that's going to fit this form, and what happens is the middle terms cancel out, and we end up with a squared minus b squared, which is the product of these two. Okay, so if we FOIL them all out, see what happens. Let's put them on here. So we have a plus b root c, and then we have a minus b root c. If we FOIL all these out, of course we get our a. We're going to get a minus ab root c, a plus ab root c, and then minus the product of those two, FOIL. Okay, that's an L. So this will be equal to a squared, and then these two multiply to give me a b root c. These two multiply to give me a plus a b root c. And finally, these two multiply to give me a minus b squared root c squared, right? It's b times b and root c times root c. Okay, but root c squared, well, that's just going to be c. At least that gets rid of the root part of it. Square root of c squared is just c. And then these two terms, we have a copy of minus ab root c plus ab root c. So these guys just cancel out, and what we have left over after that whole FOILing is going to be a squared minus b squared times c, right? That's what this is telling us right here. And the point is that we don't have a root anymore. We got rid of the square root. If these were all numbers, constants, then we would get an actual value here. But the important part is that when you FOIL these things out, there's no more root. The root goes away. That's the trick we want to use whenever we run into something that fits this form in the denominator of a fraction we're trying to rationalize. For example, here. According to the work we just did, it should be clear then that if we have 1 plus root 2, and we choose to multiply it by 1 minus root 2, and if we FOIL all of this, FOIL, 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 we end up with 1 minus root 2 plus root 2 minus root 2 squared. The middle terms cancel out, and what we have left over is a 1 minus a 2. Right? Those two cancel out, and we have minus root 2 squared, and root 2 squared is just going to be a 2. So that means that this whole thing just simplifies to negative 1. Okay, so that's what we want to do here. So we're going to come back over here, and we're going to multiply the numerator and denominator by this product. So it's going to be this, and then it's going to be 1 minus root 2 and 1 minus root 2. Right? And then we go ahead and FOIL. As we saw over here, this is just going to end up as, well, you could FOIL it all out, but if we remember our pattern is just going to be to have the 1 squared minus the root 2 squared, right? It's a difference of squares, right? They're both identical binomials, except one has a plus, one has a minus. I know the pattern is going to end up with this one squared minus this one squared. It's a difference of squares. In the numerator, I have 1 times this, so I'll just have 1 minus root 2. Okay. Now this just becomes 1 minus root 2 all over 1 minus 2, which then becomes 1 minus root 2 all over negative 1. And now, to simplify this, we can think about multiplying the numerator and denominator by a negative 1 over a negative 1. The denominators are going to be -1 times -1 equals to +1, whereas in the numerator, I'm going to have to distribute an extra -1, right? So then if I distribute a -1, I end up with -1 plus √2, which is a perfectly good answer. But I think whenever we can avoid starting with a negative, we often do. So I would probably flip this around and say that it's √2 minus 1. Okay, so that's our final answer. So kind of bringing it all together, we're saying that the original statement of 1 over 1 plus √2 is equivalent to √2 minus 1. Okay, so here's what the author did. Same thing, multiply by its conjugate, numerator and denominator by the conjugate, and we end up with something that simplifies. Okay, avoiding some common errors. Here's some common errors that I'm sure you guys will not commit. So remember, I pointed this out earlier. When we have a multiplication of two things being squared, we can separate these two out. But we cannot do that when we have an addition. Very common mistake for people to think that we can do that. If you ever run into a situation where you're not really sure, say you're in the middle of a test and you don't know whether it's true or not, just make up yourself a little example and see if it's true. If you're not really sure if this is true, think to yourself, is this true? 1 plus 3. Okay, I know that that's going to be equal squared. I know that that's equal to 5 squared, so I know the answer should be 25, right? So that makes sense. But is it true that I can distribute that squared, right? Is it true that I can take this 2 right here and somehow distribute them to the exponents like that? So check it out for yourself. So that would be 2 to the second power plus 3 to the second power. That would be a 4 plus a 9. That gives me 13. But I already know the answer has to be 25, so hopefully that convinces you that this is not allowed. Right? So just try a little side thing to see if it works. So this is not true. Also, this is not true. The square root of a plus b does not equal to the square root of a plus the square root of b. Again, just try a couple little numbers there and see if it's true. I think you'll soon convince yourself that that's not true. But with multiplication, it is. You can separate an even root of a plus b. Square root of a plus b is equal to the square root of a times the square root of b, provided that they're both greater than or equal to 0. Remember, we don't want to deal with negatives inside the square root because then that would lead to imaginaries, and we're not dealing with those just yet. Okay, so here's a couple of other common misconceptions. So just keep those in mind. All right, so that should be enough to get you started on your homework. As usual, let me know if you have any questions.